So it's a pleasure for us to present Radoslaw Szwedek from the University University of Poland, and he's going to give us a talk just about the isomorphic copies of an infinity in the weighted Hardy spaces of the unit disk. So this is something related to one of the subjects that he's an expert on. And well, I hope we will enjoy his explanations. So thank you very much.
First of all, I would like to thank Enrique and your group for the possibility of conducting scientific work here. It's always a pleasure to be here, and I see that we see the fruits of our work, and the future looks bright. So today I'm going to present one of the topics we try to understand with Enrique. This project started before the pandemic, but now we are going to present some of the outcome. And today I will talk about isomorphic copies of an infinity, but more specifically I will present why the question which will appear soon is very natural. So at first glance it appears that it's very complicated, rather and not so interesting, but then I will explain why this question is completely natural. So for instance, this question was introduced in a book of function spaces on the unit disk. I should say the modern theory of Hardy classes on the unit disk. And on the book it was written, then on the first edition of the book there was written that density is almost guaranteed by some weak conditions. I should say why that it is. But there was a slight change in the second edition, and this line completely disappeared. So we decided to take a look at this and look if it's completely clear why this question has an answer, and if it's clear, then why we were very concerned about this question, since it relates more about space. In the essence, this question has a purely foundational background. So it relates the basic concept of the theory of HP spaces, and moreover, since it is natural, I will explain to you shortly. Then we present suitable counterexamples which show that this question cannot be answered, cannot have a positive answer. So we must take a step forward from the case of LP spaces to the weighted LP spaces, in the sense of taking a step forward from HP spaces to the weighted HP spaces in order to answer that question. But I will present it soon, and the outcome of our proof is more fruitful in the sense that we can also guarantee the existence of isomorphic copies of infinity. This is more serious in the sense that we show that the structure of the space we are just studied is more. It's not as nice as it could be. It happens that it's more dramatic in the sense. So at least if you see an isomorphic copy of infinity, it means that the space is not separable, and there's no any kind of density of analytic polynomials at all, since this also is connected with separability. So I will present why this is natural. The first question should be asked, what is the theory of Hardy spaces on the disk? And I start from the bottom to the top, so I will present the basics of theory, and then I present why this can be changed, and I present two main objects we can compare, so two spaces which arise from that classical setting, And after that, I present why this question is natural. So I should start with the following definition. So we have analytic functions on the disk. So this is natural setting. So on the disk, we have almost uniform convergence on all the compact disk inside this open disk. So this is a Fréchet space, I should say. This is H. So those compact sets are smaller, and we induce a natural family of norms. But we take such functions. But how can we make suitable classes of Hardy spaces? So we take the special integral means, and those integral means provide a measure of growth of our function. So instead of taking, so we take just this integral means over such circles inside our open disk. And those provide a special measure, and the theory of classical Hardy spaces is very well known, and that means that that definition leads to several identifications. And I should start with the following two examples. So we say that function is of class HP, it belongs to Hardy space HP, if those integral means remained bounded as we approach that boundary. So this is a natural question, but there is no way, I mean that if you see the norm of Lebesgue space, you don't see at least clearly how to compute the norm of the function. So, but we do have a function which are analytic. So those are a series. And if we take a finite series, then it's easier to calculate the norm of the finite series. So it's natural to replace one object by another and approximate the series by a finite series. So the two most prominent examples of Hardy spaces are H2, which is a Hilbert space. Those are exactly spaces which are square, which those coefficients are square summable, and the class of bounded analytic functions on the disk. So there are those which are most known, and I should say that in this theory we also have nice characterization. So if this integral means remain bounded, it means that in the essence there are limits, and the limits defined at the boundary, so they are defined almost everywhere. So at least for H infinity space, every such a limit exists, and the theory also guarantees that for all Hardy spaces, those limits exist too. So this leads to another characterization. So instead of taking HP spaces, which we are taking such series and calculate those integral means, we take just a boundary function of functions from HP. And those boundary functions are just functions which lives in some Lebesgue LP spaces. So this is much easier to work with, and that leads to many generalizations and to many tools to work with. In a sense, we are interested in working with those polynomials in LP spaces. I mean that we are taking those boundary values here, and we want to approximate them by those polynomials in our torus. So this boundary of our disk is called a torus. So in the essence, we have two facts, in the sense that this script written HP, which is just a set of our boundary functions, is just a closure of analytic polynomials in LP. So this is very easy in the sense that it is much easier to work with such a structure than to work with the analytic functions on the disk. And the second, of course, in H infinity case, we need to take a weak start closure. So this is the only way when you can have such a result. But this is a classical case, and when we are thinking about classical case, we also should think about Taylor and Fourier series. In essence, we take a function from H1, and for that function we define our certain coefficients, the Fourier coefficients, and there is a connection between those. In the essence, the Taylor coefficients of a function do coincide with Fourier coefficients of its radial limits. So this provides another characterization of hard spaces in the sense that we're just taking radial limits and saying that if our function is from H1 and it belongs to LP its radial limit belongs to LP, then if its Fourier coefficients, those which in negative indexes just vanish, then the remainder is exactly boundary function of some analytic function. So this is a very deep example, and this leads to another, in other words, we can say that HP is a subspace of LP, in the sense that HP is identified with the script HP. So this leads to two separate notions. From now on, we say that HP on the disk is just classical HP with those integral means, but HP on the torus is just a set of radial functions. So this is quite different, I should say. In the classical setting, those two spaces do coincide and nothing more happens. But if we move outside the LP spaces, then they do not do so. No. Yes, stop working. Well. Yes, you may. Well, thank you very much. I was working. I should say that now I present you the definition given by Pavlovich. Those are the definitions which are suited for general hard disk classes. So not only for hard HP spaces, but for different algebras, for different set of analytic functions, for general setting. So he created this is his idea, I believe, and we take H on the disk, so those are analytic functions on the disk, and we take H on the closed disk. It means that we are taking functions which are more or less analytic on the neighborhood, so they are analytic a bit more than on the disk, open disk. So in the essence, in that space, the polynomials live. So we do also define the monomials, and of course the linear span of all monomials is the set of all analytic polynomials. So everything is defined as usual. So the definition of Pavlovich is as follows. A special class of quasi-norm vector space is called H-admissible if it's complete, as it should be, and it contains polynomials, so this class is contained in X, and that inclusion is continuous. This is very crucial, that the continuity of that inclusion guarantees that the at least pointwise functionals are bounded. So we do enjoy a non-trivial dual for that space. So everything is well suited. And then there's another definition. And it was written in the book in 2019, and the first edition of the book. And F is H-admissible if it satisfies such a condition. So that supreme on the left is bounded by the norm of X, of F in the space X. So in the sense we have two notions here. I should say that this F R C is just defined as follows. So those are functions which are a little bit shrinked in the sense, but it means that there are, if you take a function on the disk, then those functions are just functions on the smaller disk here. So it means that we are just taking a function which is a bit far away from the boundary. So you wanted to control all of them. So basically it does exactly the same. And we say that H-admissible space is minimal if that condition holds. This is very strong condition. I should say that this FR function, all of them belongs to this H closed disk space. It means that they are approximable by finite series, by polynomials. It means that they are almost polynomials. So whenever you see that condition, it means that you can take a polynomial, you can go as close as you wish with polynomials to our F. So this is exactly what we are looking for. We are looking for a density of polynomials. And so minimal spaces are always filled with polynomials in the sense that they always form a dense subset. And every minimal space by Banach-Steinhauer principle is R-admissible. So this is the strongest condition as you can get. But anyway, if you take an R-admissible space and take a closure of polynomials, all of that you can get is that following space. So that space resembles that before. It means that it may be a gap between those two spaces. So it may be some part of the space X which is not close to the closure. I should say that the question now is as follows. We have our H admissible spaces, and we can ask whether the density of analytic polynomials is related with the R admissibility of this space. So we have that. On the one hand, we have minimality, which is the strongest one. On the other hand, we have two different notions. So we have density of analytic polynomials and those R admissibility. And do they always related or not? That question is very natural to ask. It means that we also wanted to know if we can work with polynomials in our space. If polynomials are dense, then you can replace them by standard argument, paying some cost by the error. But if it's not so, then there's no hope for such a working tool. So our hypothesis was that there's no general relationship between density of analytic polynomials and the admissibility of our H-admissible spaces. So in order to do so, we need to provide suitable counterexamples. So those examples need to be taken in different setting than HP spaces. And I should say that this is the reason why we choose the weighted Hardy spaces. And the weighted Hardy spaces are also very interesting for various reasons. But for that case, it appeared that they are sufficient for proving that that question of Pavlovitz cannot be answered positively. So what we just taking is just we take a weight. The weight is always a non-negative function, and we calculate the LP space using that weight in the following way. So this is one of the possibilities here, and you use such a definition. And then we define two different notions. So for the first one, we define the HP spaces on the disk by the supremum, and Hardy spaces HP on the torus by the usual identification. So of course, if the weight is equal to 0, all we get is our classical case. So that is not the main interest here. But then both of the spaces appear to be H-admissible. So this is a nice setting to work with. But then we have a characterization of HP on the disk. It means that we can always have such an inclusion with norm 1, but in order to have an inclusion to the other side, so we have in order to have inequality, we need to have the boundness of such a limit. In the essence, it means that standard argument shows that, and this is done for Mackenhoff's weights, that using the boundness of maximum operator, which is just applied here, we can recover that this is bounded, and so those spaces are equal. So inside the Mackenhoff's weights, everything is already set. But what about the weights which, for instance, their log is BMO, but they are not in any Mackenhoff class? So this is the question now. And of course, those spaces resemble the classical Hardy spaces, but they need not be equal for weights from our set of weights. This W, I should write for you, is just a set of weights. Which satisfy two conditions. So in every case, if it's so, then we need to this theorem holds for every P. So in the essence, we produced a special weight which can be applied for every such a Hardy space on the disk. And together with such a weight, we can produce a special element of the space, which may be, which is in one of them, but it is not in the other. Okay, so this is the main result, but the proof is very simple, but it was not clear how to prove it before. And the proof of that result brings another tool, which can also be used for a more sophisticated way. So at least we can produce an isomorphic copy of an infinity. So it means that the HP on the torus is very bad in the sense that this internal structure of the space has a copy of the L-infinity space. It means that kind of spaces cannot be separated. But this is very different from the classical setting. So, of course, it is the proof of the theorem 2 is much more complicated than theorem 1. But I start presenting with theorem 1. But now I should say a few more words about the question of Pavlovich. So in the essence, we should start with the following remark. So in the classical setting for Hardy spaces, we have the Berling's theorem, which says something about weights from this Szegö class. And this Berling theorem can be applied for weighted Hardy spaces on the torus. This is exactly what is this theorem about. And this says that analytic polynomials are always dense. In the essence, the Berling theorem says more about the density of certain sets and says about the density of analytic polynomials. But then it is by our theorem, this is, I should say that HP on the torus is quite different from the HP on the disk. But then this HP on the torus is again an example of an H-admissible space which is not R-admissible. Why is that? So we know that the analytic polynomials are dense in the space, but if that space would be R-admissible, it would follow that those two spaces are equal, but they are not. So this cannot happen. More or less, I should say that HP on the disk is always R-admissible, and this is following from the definition just by one line. So this is easy. But we just said that this is not a separable space, so the space cannot be minimal, and the analytic polynomials are not dense in that space. So more or less, we have a couple of two spaces. One of them is R-admissible, but the analytic polynomials are not dense in it, and the other is R-admissible. It's not R-admissible, but analytic polynomials are always dense in such spaces. So those are two spaces which are completely different from each other, and it means that this question of Pavlovich's very natural question cannot be answered positively. There are no general relationships between the density of analytic polynomials and the R-admissibility of H-admissible space. So this is, I hope that I convince you that this is a very natural question. So the question about the density of analytic polynomials is a question about the structure of the space, and those spaces do have very bad structure, those on the disk. Okay, so I should start with some idea of the proof. And the first idea is as follows, that we are looking for a counterexample. So we are just looking for a function which is on the HP, weighted HP spaces on the torus that satisfies such a condition. So that cannot be in HP on the disk. What the idea of construction such a weight as such a function is very connected with estimates we can do in classical harmonic analysis. But then we should take a special rearrangement of our elements of a torus. I should say that we create a special partition of a torus. So on the torus, we divide torus in that way that we have a smaller and smaller set of we have a set of intervals on the torus, and we control the diameter of those integrals, and in some very precise way. But then we create a special weight. So what you see here is just the characteristic function of those elements of that partition. But then here it is a very small value, and here is value 1. So we have created a weight which is locally very, very small, and then again as big as we wish it could be. So 1. So it's very small, 1, very small, 1. And so this weight is very special. In essence, that weight does not belong to any Markov class, but we can estimate its logarithm. So we create a special, we just created a special weight, and obviously you can calculate the weight against the L1 and L log norms, so we can calculate them, and everything is bounded. It means that this weight is from that class, so HP on the weight, on weighted Hardy space on the torus is well defined, at least in that space, so we can work with that. Obviously, it means that we can define a special function. So this is the Otto function. This is a very classical thing in Hardy. It's classical thing in harmonic analysis in Hardy in theory of Hardy spaces. But those are exactly functions of the form. So we can calculate those functions directly. And as you might expect, the radial limit of such a function is just the value of that weight. So whenever we take such a function and goes to the boundary, all we get is that weight. So this is a very nice function to work with. And obviously, this function, as you may see, it is very, very big on some small intervals. And again, it's small. Very, very big and small. It means that we are going to play with the weight against the functions, or vice versa, to make some estimate very, very big. So, in essence, all you wanted to show is to estimate the Poisson kernel in a appropriate way. So we take a special family of subsets, which has just the subsets such that our Poisson kernel can be estimated from below, and this is the only purpose of such a family. And as you may see, that Poisson kernels have some nice properties. And locally, we can always find such a subset, that such a values that our Poisson kernel is big enough, I should say, in order to fulfill our dreams. But now, if you take such an estimate of the norm, and you have exactly you have two integrals here in the way not to introduce the too many symbols, but this is an arc length. So don't worry about the symbols here. But we have two integrals here. But we can always take a smaller one here. So instead of the torus, we just take this Jn, and instead of the torus here, we just take a special element from our initial partition. Okay, so it means that we can plug our estimates here, and we estimate that expression here by, so this Poisson kernel by 2 to the power n, and that is completely easily calculable. So you can compute that directly, and all you get is just the following estimate. And as you see, this estimate shows that those numbers tend to infinity as fast as we wanted to have. It means that there is no, that element cannot belongs to HP on the disk. So there's no hope for that. But the proof is very, very nice, but of course this is very easy if you know how to take a weight and compute that. So the proof is just one slide, but one way. But we can use it in a more sophisticated way. In the essence, we can prove that we can separate elements from each other. So we can choose elements from the space which are well separated from each other in the sense of the norm. And this is the main idea of the proof. And this is the proof of the second theorem, which says that we are able to construct an infinity copy of in HP on the disk, this weighted one. So we have 3 parts of the proof. So from now is my 10 pages of the proof. So don't worry about everything you see, but this is a very nice idea, but very easy if you don't look at the details too close. In the sense, the main idea is that we take a functions, but we take a special family of those ways, in the sense that we take function generated by those expressions. So the weight HP weighted is the same as before, but the functions are different. So we only have one bump, especially one bump. And taking a function bump is higher, but this is not so wide as before. And this is the idea of the function. And as we approach the boundary, such a function tends to the function we define the other functions. But this is very, very small in the sense that this part of the torus, this part of the partition is very, very small. Since by Szegö theorem we can estimate by above whatever you can take, in the sense that this in the norm of weighted LP spaces can be very, very small as we wish. So, in that sense, we created the functions, but this function is it's not such a restrictive function, but for every n, those values are very small, but the values of that limit goes to infinity. It means that whenever for each n is from the H infinity space, so that it must be bounded in any different HP space, but it means that we can control them locally. We cannot control them all since this limit goes to infinity, but locally everything is well defined. So if we fixed n, everything is okay. So if we fixed n, for instance, we do have a mean convergence theorem, which is a very classical fact that those tends to those radial limits. So this functions which live on the smaller disk tends to the function which lives on the this torus in the LP weighted norm. It means that we have some control here, but this control is depends strongly on n. So whenever we take a bigger n, we need to take r which is far closer, it's more closer to the boundary than before. So it holds as a limit, but it means that error, the distance must be much shorter than before. Okay, so everything works correctly, and everything works on the boundary. On the boundary, we have everything is bounded by 1, but here we have infinity. So it means that the function can be as big as you want on the smaller disk, but on the boundary is very, very small. it's not, and very, very small in the sense of LP norm. So it does not contradict anything. But now, since these functions are just finite in the norm of HP on the disk, we can normalize them and everything works correctly. So now you see that this is actually going to 0, and here you also have a control over that, and you also do enjoy this mean convergence theorem. So everything is working correctly, and those are functions which are taken preferably to have to obtain this well-separated set of functions. Okay, so we are just taking some epsilon. So those epsilon are just taken in order to have some nice estimates. So don't look at too much at those. This is just a special way of writing them. So we just wanted to select a sequence of appropriately separated functions. So in essence, the first step is very easy. We take a special as the first function. We take a function which is very, very small at the edge and very, very small near the center of the disk. It means that this is our case here. So the function is very, very small here and very, very small here. But we know that this function, that function is normalized, that it must be equal 1 on some circle here between those two disks. So we need to choose R1, which is between R0 and R1. So again, it means that we need to choose such a disk. When this control is always side. Okay. Of course, so the basic idea for that is as follows. As this is smaller than epsilon 0, and we have the mean convergence theorem, we can get very close to this boundary region by some R1. So not only everything is small on this smaller disk, on this boundary, but it can be very small on this other disk. So we have situation to have very small here, and very small here. So this is here very small, this is very small, and here it can be very, very big. Actually, this is as big as we produced that function before, so it's equal 1. So at this boundary, of this part of a disk, we just want to choose another functions. And another one is chosen as to be not as to be smaller than epsilon 1. So again, we take another function from the set of function G, n, and those functions are very, very small at the edge, at the boundary of our disk, and very, very small inside of the disk in the sense of those R1 disks. So here this function is very small, and here it may be very big. And again, we take a special circle here, and I can say that here that new function is very, very small, and here this is very, very small, and that on that region, on that only the function is the norm of the function is equal 1, and that when we separate them continuous way in order to get a sequence of functions which in the norm are in the way we calculate the norm of the hard HP on the disk spaces is using the supremo. So we actually divided interval from 0 to 1 into some pieces. On each one you can estimate those functions by epsilon 1 or just by 1. It means that we can proceed by induction, and by induction we produce a special family of functions. And the first thing is obviously that if we define such a function which you see here for every sequence, I should say something about if it's well defined, but it is so. In essence, we have some nice estimates of that function. It means that we can estimate those elements by elements of our sequence and by some epsilons. So in essence, by above, we get estimate by norm of lambdas in an infinity space and some constant. So that is one part of the solution, and the other is to prove that this is a well-defined linear operator, and what is actually needed here is just the statement that this is a partial isometry. So we need a lower bound, and this can be also done by calculating the norm of the spaces. So we also have such an estimate from below, and this is actually well defined in the sense that whenever we do choose such an epsilon such that series is converging to numbers which are strictly smaller than than given epsilon. So you can control every element of that series. And after that, we get that this is a partial isometry, and we get what you want. So this is an infinity structure within the HP on the disk space. And that's all. That's all what I wanted to say today, and thank you for your attention.
So thank you very much for your nice talk. Is there any question or comments or?
Okay, in the proof of theorem 1, you have done a partition of the dollars.
Yes.
It's just a curiosity. Let's see. Yes, here. For instance, you are taking the first set, I0, and you start with these two. Which is the role of these two? Because I think this is, you have some kind of freedom, not choosing.
So the first one is just
why from 2 exactly to 2 pi? I mean, these two or whatever. It could be another.
Yes, I mean that we wanted to have, if I write as an interval on here, so here we have, let me write 2 pi, and here 0, better. Then the first one is just 2. So I just not intend to write as a pi, but I write as a variable of t, so it's a bit easier. So instead of taking a torus, we are just taking an interval from 0 to 2 pi. So this is a bit easier to work with, but this is written in such a way to have some estimate. So this is the only problem. And then just taking a family of those, yes, taken in such a way that we have one of them is have pair of those intervals. Those intervals are equal in the length, but each pair is about have some doubling constant. So each pair is twice as smaller than a pair before. So this is the main idea, to take a decreasing set of those pairs. So, but then we're creating a weight, and the weight is as follows. We also have the weights is in such a way that those smaller is higher and higher. But in the sense, there are very those elements of the partition can be very, very small, but the value of the weight can be very, very high. So this is the only reason we choose such a construction. We wanted to have a function which is can be very, very high during the calculation of HP on the disk norm. So this is the main idea of the first one.
So you have chosen to do a little bit more on the right or on the left?
Yes.
As long as you keep the same construction?
Yes, as long. So this is an infinite construction in the sense that we are just, in the classical case, this does not work at all, since the norm are just converging to each one of to the other. But in such a construction with the weighted case, this weight explodes the norm. So we can always, using this estimate, we can see that we have some kind of explosion here. So even for those very, very tiny little bits, we have that this go to infinity. But I even calculated this for all the tolls, for all points. So this is sufficient. So partition-wise, this I would have chosen a few bits of that partition and work with, and everything which would work as before. But this is an extreme case of such a weight, and it answered the question. It's maybe the best way to do it.
So, thank you very much. There are more questions or comments or whatever? No? So, we thank again, speakers.